you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, this is Mr. T, and thanks for joining me today on our tutorial. Today we're going to be talking about polynomials, and in particular things about polynomials called zeros. Zeros are also the same as x-intercepts. So on this polynomial that I have graphed here, this is the equation here, so it's a quadratic, we have two x-intercepts. Those are the zeros. Now what's important for today's tutorial is looking at and understanding the relationship of these x-intercepts, or zeros, and the factors of the equation. Zeros, or x-intercepts, are always on the y-axis, and if we look at the points on the y-axis, they always have a y-coordinate of 0. So if we put 0 in for y and solve that equation, what we are finding are the x-intercepts. So here we have the x-intercept here, and here again we had this x-intercept. So there's a strong relationship between factors, solutions to quadratic equations, which are the zeros of the quadratic equation, and the x-intercepts on a polynomial. So we're going to be exploring this in a little bit more depth today. So again, as I just said and we showed graphically, if we know that a particular number is a zero or x-intercept of a polynomial, then we know that x minus that number is a factor of f of x. And conversely, if we know a factor, x minus p, then we know that the solution of that factor equals to 0, which would be p, is a 0 or an x-intercept of the function. If you remember back on our last video when we talked about polynomial division, if you evaluate a function at one of its intercepts or zeros, you get the value 0. And also, if you divide a function by a factor of a function, you get a remainder of 0. So we're going to be using that as we go forward. Okay, on this I've got several graphs here, and what we're going to try to understand is the relationship between the degree of a polynomial. If you remember on our discussion of polynomials, degree is the biggest exponent when it's in standard form. And we're going to look at what the degree tells us regarding the factors of a polynomial and the zeros. Here I have graphed three different polynomials. The equations are shown here. So this one goes with the one in the middle, this one goes here, and this one is here. If we FOIL these out, these would all be polynomials with a degree of 2, because they would be x squared when we FOIL them. All three of these polynomials have the same two x-intercepts, the same zeros, 1 and 4. So one thing this shows, which we'll be using later, is that we could have lots of different polynomials with the same zeros. So if we know the two zeros, we can turn them into factors and get a polynomial that goes through those zeros, but there could be lots of them, and I could, by changing this a value, we could create lots of them. In this particular example, you can notice we have a polynomial of degree 2, and we had two distinct zeros. On our middle graph here, I've graphed this polynomial, which if we FOILed this out, we would have a cubic polynomial, a polynomial of degree 3. And on this one, we have two zeros. This is at 1, and this is at 4. So in this case, we have a degree 3 polynomial, and there are two distinct zeros. So we have the number of zeros is less than our degree. But this polynomial, if we expanded it out, the x minus 1 would be repeated twice. So this 0, the 0 of x equals 1, is said to have a multiplicity of 2, or meaning it's repeated 2 times. If we count that as 2 separate zeros, then we've got a degree of 3 and 3 zeros. And our third example here, we still only see 2 distinct real zeros. But if we FOIL this out, we would have a degree of 4, and if we expanded this out, we would have x minus 4 3 times. So this 0 at x equals 4 has a multiplicity of 3. So if we include multiplicity and count each of those zeros of 4 3 times, so if we counted our zeros as 1, 4, 4, and 4, we can see that we have the same number of zeros as our degree. Kind of when you're looking at a graph, if you see a x-intercept where the graph comes up and touches that and then goes back over, that's indicating that this 0 has a multiplicity and that it has a even multiplicity. So this could be a multiplicity of 2, 4, 6, etc. When you see what's this sort of zigzag shape here, which is called an inflection point, or a turning point of a function, when you see that on an x-axis, that also implies that there's a multiple 0 there, and that multiple 0 would be a odd numbered multiple 0, like 3, 5, 7, etc. Now let's look at one more example with the picture. Here we only have 2 zeros that are visible on the graph, and this was the function that we graphed. So in this case, we have 2 real zeros, and if we solve this equal to 0 to find other zeros, we would get 2 complex zeros. This would be x equals I and x equals negative I. So sometimes our zeros could be complex numbers. When we include complex numbers, then we're going to see on the next chart, and if we also include multiplicity, we're going to see that the number of zeros of a polynomial, because this would have degree 4, if we factored this out, we would have an x to the 4th as our leading term. We've got 4 total zeros. Another thing to keep in mind with complex zeros is that they always come in conjugate pairs. So in this case, we've got plus or minus I as a pair. Remember, a conjugate, if we had 1 minus 2i was a 0, we would also have a 0 of its conjugate, which would be 1 plus 2i. We take the opposite of these signs here. Now that leads into a discussion of one of the basic theorems of algebra called the Fundamental Theorem of Algebra, and it also has a number of implications. So the theorem is stated here in purple. If f of x is a polynomial of degree n, then that equation, if we solve that function as an equation equal to 0, has at least one solution, or one 0, in the set of complex numbers. But for me, what's more interesting is what's going to be down here. So we saw when we are looking at real zeros, the number of distinct real zeros is going to be less than or equal to the degree. So if we go back to our pictures here, we had 2, so that's less than or equal to 2. This was a cubic, and we had 2 distinct zeros. Here was a quadratic, a quartic, a 4th power. We had 2 zeros. So the number of distinct real zeros was less than or equal to the degree. But when we counted zeros including repeated zeros or multiplicity, and if we found the complex zeros, sort of what's important for me is that the number of zeros will equal the degree. So when we are solving say a polynomial of degree 5, we should be looking for 5 zeros. The complex zeros always come in pairs, so there will always be an even number of complex zeros. So if we had a cubic, say an x cubed, so f of x was a polynomial of degree 3, we could either have 3 real zeros. Now they could be 3 distinct real zeros, or it could be a 0 of multiplicity 3, or we could have 1 real 0 and 2 complex zeros. By this fact here, it would be impossible to have 2 real zeros and 1 complex zero. It would also be impossible to have no real zeros and to have 3 complex zero, because the complex ones always come as even numbers. Now we're going to be using graphing calculator for finding the real zeros. So I'm going to bring us a graphing calculator. And to demonstrate that, I forgot to turn on my calculator, we're going to use this polynomial here. So this is a x cubed if we FOILed it out. And this is a printout of that polynomial. Now sometimes we can see from the graph. Now when we want to graph something into the TI 84 or 83, we press Y equals this button and we type in our polynomial. And then to graph it, we could press graph, but I want you to use zoom 6. So we're going to press zoom and 6, which is standard. And what that does is it sets our window up here to go from -10 to +10 on the x-axis and +10 and -10 on the y-axis. For the examples we're using today, this window will be satisfactory. When we work on some more advanced graphing, we can go into Window and we can manually set how far to the left we want the x-axis to go using xmin, how far we want to go to the right using xmax, and we can adjust the y scale of how low or high we want that to go. Now to find the zeros, we're going to use this calc option on the graphing calculator. So to get to that, we have to press, since it's in yellow, the second key. So second, calc, and the option here is 0. Now remember that 0 is the same as x-intercept. So if you had a problem that said find the x-intercepts of this function, we could use this. Now to use this function, it's going to ask us for 3 questions. It's going to ask us what's the left bound, then the right bound, and then a guess. So I've shown on here, at this point here, I put a vertical line through the 0. So left bound means it wants us to move this cursor, which is blinking here. It wants us to move it somewhere over here, somewhere left of the 0. Sometimes left of the 0 could be below the x-axis. Up here, when we find this one, it could be above. So left doesn't mean you can't depend on whether it's up or down. It's being left or right of the point we're looking for. Now there's no way to find all 3 zeros with one command. We have to do it repetitively. So I'm going to find this 0 first, so we need to move the cursor over here. Now when you move the cursor, we only use the left and right buttons. If you use the up and down buttons, it's going to mess things up. So we want to go left. We want to go to the left past our 0, so that's there. Now we press enter. Now we need to go to the right of our 0, so we just need to go through the 0. Press enter. And then when it says guess, you can just press enter. You don't need to move anywhere. And it tells us our 0 is here, and it's an irrational number, so our 0 here is negative. We'll round it to 2 decimal places, 2.24. Now if we go to find the next one, I've just got to repeat that process. So we've got to do the second calc 0. Now we need to move it left of the next 0, which would be somewhere in there. Enter. Now we go past the 0, press enter, enter, and now we've got, this one is at x equals 1. And to find our third one, we need to put the left bound, which would be, say, there. Now we need to go past the 0, press enter, enter for guess, and we get about 2.24 positive. A shortcut that you can use to make it easier, if you look at the tick marks and if you think a 0 is on an exact integer value, we can use the table function. So if I go second table, it gives us a table of the table of values for this function. And x-intercepts are zeros, or where the y is 0. So we can scroll through this list and we see that we get y is 0 at x equals 1. So that was that one. So you have two choices for finding zeros. If they're nice numbers, integers, we can use the table. And to find the ones that are fractions or irrational numbers, we use the second calc 0. Now we're going to tie together here a number of things. We're going to tie together what we did in synthetic division. We're going to tie together what we've learned in this video regarding zeros. And our objective is to find all the zeros of a polynomial. Now the graphing calculator can only find real zeros. So if a polynomial only has real zeros, we'll be able to find them using just the graphing calculator. If the polynomial has some complex zeros, we're going to find the real zeros first using the graphing calculator. We are going to use synthetic division to factor out all the real zeros, and what remains after we've divided out or factored out the real zeros will be a polynomial, which for us will usually be a quadratic, and we'll solve that algebraically using either square roots, completing the square, or the quadratic formula to find our complex zeros. So I want to go through 3 examples here. Here's the first one. I'm going to pause the video while I type in the formula so I don't drag this on too long. Okay, I've entered our graph. Let's press zoom 6. Now we can see here that we have 3 distinct zeros, and it's a degree of 4. So we know we should have 4 zeros if we include multiplicity and complex zeros. So since we have 3 distinct zeros, we know that we can't have a complex zero, so we have a 4th real zero. And this pattern here tells me we have a multiplicity, so a multiplicity of 2. So I need to find these zeros. Now I'm going to do this when they look like they're in good shape. We could use the thing we did earlier with the graphing calculator, second calc 0, but I'm going to save time on the video, use our table and scroll backwards here. So we see at -3 we have a 0, so one of our zeros is -3. We have one at -1. And if we go forward, we have one at 3, +3. Those were the 3 distinct zeros, and this one at -3 has a multiplicity, so we could list -3 twice. So let me just add that into the front. So we have a degree 4, and we found 4 zeros, -3, -3, -1, and 3. And since we found 4 real zeros, we are done here. We don't have to do any of the synthetic division. So let me pause the video and put in our second example. Okay, here's our second example, and I've moved to a clean sheet here so that we can work. Let's press the graph. Now we see 1 0 here. Now we could solve that using our table. It looks like it's a integer value, but let's just refresh one more time using the second calc 0. So I need to put my left bound somewhere over here. So let's move it to the right a little bit. Now sometimes on really big polynomials, this cursor may not ever show up on the screen. It could jump from down here, and then you click this one to the right and jump up here. Down here, it's giving you the coordinates, the x and the y coordinates of where the cursor is. So we see that we're still down below, but now we can see it coming here. So I'm going to press enter. Now we need to go past our 0. We just went past, so we hit enter, enter, and we get x equals 1. So that's our real 0, and that's the only one we can find. So since we found 1 real 0, that tells us that a factor of this is x minus 1. And since we found 1 0 and it's a cubic, that tells us that we must have 2 complex zeros. So I need to divide this polynomial by -1. So I'm going to use synthetic division. So we put our 0, which is 1 here. We put our coefficients. Remember, if any of the terms, the x squared or the x was missing, we have to fill in zeros. We bring down the 1. 1 times 1 is 1. Now we add. 0 times 1 is 0. Add. 25 times 1 is 25. We get 0, which is good because remember that's the remainder. And since we knew this was a factor, we should get a remainder of 0. And then this represents x squared plus 25. And if we want to find the zeros, we set that equal to 0. And we can solve this one using square roots. Square root both sides. Remember your plus or minus. Now since we have a negative under the square root, we know we're going to get a complex number, an I. And the square root of 25 is 5, so we've got plus or minus 5i. And we have x. So our zeros, all of our zeros are 1, positive 5i, and negative 5i. So we have, again, a cubic with, degree 3 and 3 zeros. Now let's move on to our last example. I'm going to pause the video here while I enter the last example. Okay, I'm back. We have our last example in the calculator, so let's graph it. Now we're looking for 4 zeros here. And it looks like we see 2 of them on the 2 real zeros, and it doesn't look like a multiplicity, so let's find the 2 real zeros here. So let's do second calc 0, and now we need to go left of the first 0, which will be above that over here. So we're still negative on the y. Okay, we just jumped over, so here we're up here somewhere, so let's hit enter. Now we need to go past the 0, so now we're negative, so we jump down here, press enter, enter. So we have a 0 at negative 5. Is our first 0. And let's find the one over here. Now let's just save time, so let's go to the table because it looks like it's a real 0. So we have one at negative 1. We could have also again found the negative 5 that way. I'm just trying to get you to understand or see the graphing calculator technique because many times we might not have real zeros. They might be irrational. So now there are no more real zeros on our graph, so let's divide these zeros out using synthetic division. So I'll use the negative 5 first. It doesn't matter which order you do these. So now we've got 1, 6, 14, 54, 45. Bring down my 1, so I got negative 5, 1. Negative 5 gives me 9. 9 times negative 5 is negative 45. 9, I get negative 45, and I get 0, which is my remainder. And that's good. If you don't get 0 here, then either you didn't find the zeros here or you've made a mistake. Now we need to factor out or remove the negative 1, 0, so we have to repeat this process. Now this is these are the coefficients of our cubic after we factored out the x plus 5. Zero here, we get 9, negative 9, 0, which is, again is good since we knew it's a factor. So again, I got one that could easily be solved with square roots. You'll see if you solve that, we've got x squared equals negative 9 and x equals plus or minus 3i. Now, it could be that this may not be a sum of 2 squares. It could have an x term in here, and again, you could use quadratic formula or completing the square to find those. So now, if we add our 2 complex zeros, we have again a degree of 4 and 3 zeros. So good luck solving your polynomials, and see you the next time.
Are you ready? Are you ready?